limit of a sequence, we'll have different limits in all the different coordinates, and we have to take n to
Just
infinity.
one moment.
And
I'll just one.
yes, sir. Sure.
Try to manage something that is streaming. Yeah, please go ahead. We were talking about limits of
Limits sequence,
sequences.
yes, yes, sir.
Okay.
So we'll have different kinds of sequences in all the coordinates, and we have to extend n to infinity, and we have to see the limit. That's it, no, sir?
Yes, and only if each of the
All of
coordinate
them exist simultaneously.
sequences have limit, yeah,
Yes.
only then
All
will
right.
your sequence in Rn have a limit,
Right.
and that limit will
And
also be in that corresponding Rn. Yeah.
sir, difference between a limit of a sequence and a limit of a function is that sequence we only put numbers one, two, three, all the natural numbers, while
Yes.
in for function we put all real numbers. Is that a correct statement, sir?
Yeah, in a way, yes. So, and typically you take when you're talking about the function and the limit of the function, you take this x going to some x naught in the domain. But here
Right.
you're just looking at you're looking at a set of numbers, and this sequence is infinity. So it's not like you're inputting something. Well, you could think
Right.
of it as a function on the set of natural numbers, and then you're taking it to infinity. But this is not really a point on the domain. You're not taking your variable to some point on the domain. You're just analyzing the behavior of a sequence of numbers.
Right.
So,
Makes sense. S-
yeah.
Sir, in a we have learned in multivariable functions.
Hmm.
Uh, Suppose, let's say, could you please write this down, sir? Limit of
Yeah.
x tends to 0 comma 0, x tilde tends to 0 comma 0, or
Okay.
same thing, sir. Yes. X of y, xy divided by root over x square plus y square. So,
Okay.
sir, ma'am previously told in our lecture that we should analyze what this thing approaches from y is equal to x axis, y axis, y
Is it
square is
square root
equal
of
to
x square
x.
plus y square, or is it just x square plus y square?
I don't remember the exact questions. I forgot to note it down.
Okay. Because
Uh,
for just x square plus y square, you will not have a
right,
limit, but for square root of x square plus y square, you will have a limit.
right. Makes sense, sir. Sir, so how
Sir,
do we know?
how do we have limit for root over x square plus y square, sir? Could you prove
You
it?
want me to give the proof?
Yes, sir.
Uh, it should follow from some okay, AMGM inequality kind of thing. It should follow, but let us just look at this thing. This x square plus y square minus 2xy. Let me just take it. This guy is always going to be 0. So xy. No, but you want not square root of this one moment. Square root of x square plus y square. This is greater than or equal to x. Therefore, I'll explain the steps. Just writing this down. So do you know why this happens? The square root of x square plus y square is greater than or equal to mod x.
Yes, sir, because we're adding definitely a positive number
Yeah.
to mod of
So
x, something like that.
if I remove if I replace y square with 0, y square is a positive number, right? So x square plus y square will have a larger square root than x square plus 0. But the square root of x square plus 0, this is exactly equal to mod x, right? So mod x is less than or equal to the square root of x square plus y square. I've just rephrased it like this, and then I divide by square root of x square plus y square. Square root of x square plus y square is a non-zero number. We are approaching 0, comma 0. We are not at 0, comma 0. So this identity is satisfied in a neighborhood. Is that okay? I've just divided it by
Sir,
square root of x square plus
uh,
y square.
uh, we know a method where from lectures we have seen where we see through x-axis or y-axis or x equal to y. If I do in that way, for x-axis I get 0 and for y-axis I get 0. For x equal to y I get, since both are equal,
You will
oh
still get
sorry.
0. So here, if you put y is equal to mx, you will get x times mx divided by square root of x square plus m square x square, which is nothing but x square m divided by modulus of x times some constant. It's like square root of 1 plus m square or something. But here you see that x square by mod x, this will go to 0. So it does not matter which line you approach it from, the limit you will get is 0. But that is not sufficient to say that the limit itself is 0. So there are two things. If you want to show that the limit is not does not exist or is not equal to something, you can take two different lines and say, if you get a line along which the limit does not exist, then that is enough to give the negation that this limit does not exist. Or if you find two different lines along which the limits exist but are different, that is also sufficient to say that the limit does not exist. But to actually prove that the limit exists, even if you say the limit along every line exists and is equal to the same quantity, that is not sufficient because you need it via through all curves. That is the correct statement. Or alternatively, you will have to try to use the sandwich theorem, which is what I'm trying to do
Yes,
in
sir.
my algorithm
I
over here.
understood, sir. I made a small mistake. I couldn't cancel out.
Sir,
X
could you please
was
explain that
in the numerator.
statement where all curves should approach the same point?
Not
I
all
did
curves
not
should
understand.
approach this. So along all curves, the limit should. So if I have, so this is a function in R2, right? This is a function from R2 to R. So
Right.
the domain is R2. So and
Yes,
I'm
yes.
interested in this point, the center, the origin,
Sir,
and
domain is restricted to it's not 0, comma 0, r minus 0, r square minus.
okay, sure, yeah, r square minus 0, comma 0, but I'm interested in the limit as it approaches 0, comma 0,
Right,
right?
right,
So I have to analyze the behavior in a neighborhood, and
right.
the alternative way is you look at all possible curves to it, and that's a huge space. Like if you look at all lines passing through the origin itself, there are infinitely many of them. But even that is not sufficient. You need all possible curves. So for example, you if you have this, whatever this is y is equal to x square. Along that curve, also this quantity. So if I put y is equal to x square in this, I'll get x times x square divided by square root of x
Sir, sorry to
plus x
interrupt,
to the
sir,
4. Just one
but
moment.
if
Let me just.
yes, sir.
This is for y is equal to x square. Even then, the limit should be the same.
Right, sir. But over here, you just if you substitute y is equal to x square in this, you're finding the intersection point, no, sir. How is this correlating to if you're approaching through towards the
No, no,
curve?
no.
I did not
The
get that as
points,
well, sir.
the points on this, the generic point in this is x comma x square, right? The point on
Right,
the graph
right.
of this curve. So I
Yes.
approach 0 along this curve, meaning along points of the form x comma x square. So instead of this is say f of x comma y, I'll use f of x comma x square.
Sir,
So
so
when
all
you're
do all the points on this y is equal to x square lie on the function?
no, no, no. So there are this is the function whose limit you have to evaluate f, right?
Right,
And your domain is a neighborhood of your limit point. In this case, it is let's say r2 minus 0, 0 itself. Now, what are all
right.
possible? So this y is equal to x square. So gamma of x is equal to x comma x square. So this, okay, gamma may be confusing. Let me just put g of x is equal to x square.
Right.
Now, this is a curve which passes through the origin.
Yes.
Now, along this curve, I have to evaluate what f of xy is. That is, I have to look at what f of x comma gx is,
F of x comma gx. Okay.
which is f of x comma x square. So, okay, if this is too confusing, you see, you would recall what you were doing while taking it along the x-axis or taking it along the y-axis or taking along the line y is equal to x. What would you do? You just put y is equal to x, right? So you will get this x square divided by square root of 2x square. And then you argue
Right.
that this what are you actually doing? You're just evaluating the limit of this function along the line y is equal to x. Now instead of the line y is equal to x, I take it along the parabola y is equal to x square.
Okay. So sir, are we basically saying in the neighborhood of 0 comma 0, basically the parabola and that same point, it's almost the same. The function is almost the same, something like that.
No, 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 no. It does not matter what curve I consider which passes through the origin.
Right.
The function, when restricted to that curve, will approach the same limit, is what I want.
Okay. Makes sense. Yes, sir. Yes, sir.
So,
Uh,
Makes sense.
what is two-dimensional behavior? So, when we jump from one-dimensional to two-dimensional thing, there's something much more than uh, ordinary happens. As in one dimension, you have only right-hand limit, left-hand limit. You have only two directions to approach. When you jump to two
Yes.
dimensions, you have an infinite number of directions. Well, infinite
Right.
number is not a precise way to say it, but yeah, there are infinitely many directions that you can approach. But even
Right.
that is more nuanced in the sense that you cannot only consider all the straight line directions. All curved
Right.
directions are also you have to consider.
Makes
To
sense.
highlight this point, I will give an example at the end if there is time.
Right, sure, sir. So one more thing, just suppose if this question was saying limit x tends to 3 comma 1, then we cannot use this curve method because all these curves and lines through the origin pass through the origin and not 3 comma 1.
Yeah, you have
Right,
to
sir?
consider all curves passing through 3 comma 1. Yes. Well,
So we
in
have to
this case,
always,
you can just get substitute the 3 comma 1. But yeah, I get what you're saying. If there is something that vanish like which is not defined on 3 comma 1 and you want to say that its limit exists or something,
r-
you have to
right,
consider all curves through 3 comma 1.
curves on that single point. Right, sir?
Curves through that single point.
Through that single point.
Yeah. Yeah. Yeah.
Okay, sir. Sir, one more thing in the professor's lecture, he was explaining that f of any limit that's going from x to x to some any limit that is going from for a multivariable function to some single variable,
So it's
you
like
can just
R
substitute.
into R, the
Yes, yes, the scalar sir, could you
scalar
please
value
write
multivariable function.
limit
Okay.
of x tilde going to let's say a comma b comma c
Fine.
or
Some fixed point. Yeah.
x,
X not
yes,
zero.
yes.
Yeah.
And the function is xi to the power of n, any point, or x1 to the power of n, anything. So
Okay.
in this function, the professor clearly explained you can just substitute if it's smooth and continuous, and if that
Hmm.
point it is existing, you can just substitute. So
Yes.
how do we know when we can substitute and when we cannot? If it's not in indeterminate form, we can definitely substitute. Is that a correct statement? Can we always substitute?
Yes, you can substitute when the functions are well behaved. And yeah, this is what you are asking, right? What is well behaved? So, for example, what is this? This is a product of n-fold product of xi. So
Right,
you know that projections are continuous. You know multiple products of limits are limits of products. So
right,
there are things that are happening in the background which allows you to do the substitution. And
right.
beyond that, you just substitute and see. If you don't get an indeterminate form, then you're fine. Most of the times, this will work, at least for this course. It may not be
Right.
completely precise, but the
Okay.
kind of functions that you will deal with, you will not have a thing where uh, this thing is so badly behaved.
Okay, sir. Makes
Typically,
sense.
where you will have problems is you this function will be defined in a neighborhood of the limit point, but at the limit point, if you just substitute, you will
Then
not
it'll be
have
0 by 0 or something, some indeterminate form. So,
yeah,
sir,
yeah.
the lecturer just combined the limit. He said limit properties like f of g f plus g of x is equal to f of x limit. So limit we can just distribute through sum and product. So
If
that's how
both
you
limits exist,
combine
yes.
if the limits exist. Yes. So
Yeah.
that's how you combine multi-variable with like single variable. Is that correct, sir? That's how we went from this to a polynomial, like x1 to the power of n
Right,
plus
right,
x2 to the
right,
power
right.
of n.
Yes. So if you know that each xi, the limit as x tilde goes to some x naught tilde, this exists, then you can use
Right,
multiplication to get monomials of whatever order. Then you can use the sum
right,
property to get polynomials of every order. You can use the scalar
right. And
multiplication property to get all
and
coefficients and all that.
right, and division is only thing, the denominator should be non-zero. That's it.
Yes, the limit of the
That's it,
denominator sequence.
sir.
Yeah,
Thank you, sir. Thank you.
yeah.
Appreciate it. Thank
Okay, sure.
Sir,
Yes.
in this way that you told to check the limit existence of a function, we have to check through each occur. So in this
So
way, we can
that's not
disprove
a
the
way
limit.
to check.
Hmm.
That's not a way to check because taking all possible curves is not practical. So if you want to disprove, it may be a way. You can choose a nice curve such that this limit does not exist. But in order to prove this will not be useful, you will have to use something like sandwich theorem, as we did over here. So, okay, one more thing. Did you guys understand this part?
you. Yes, sir. Sandwich theorem, sir.
Yeah.
Sir, how to interpret this?
How to interpret what?
So final part, 1 second. Could you just tell? I understood till final part, but from there,
Uh,
how do you apply sandwich theorem?
Just take limit as xy goes to 0, 0 on both sides. This is just minus y, right? So this is just like xi.
Oh, yes, 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 yes.
It's
So
like
it's just
x2.
zero.
That should be 0.
It
That will be 0.
so both are zero, therefore that is zero. Okay, sir.
Yeah. If the limits on both sides of the inequality is 0, then the limit on the center also should be 0. But it need not be 0.
Right,
As long as both limits are equal, then the limit of the center expression in the middle is also equal to that limit. So, okay, I think we
how
should
do
get
you,
started
how do you
on
choose the
detail.
like the what is to be sandwiched? That is the if I
Yeah,
have a new problem,
there's no well-defined way to do it. Typically, you will see that whenever you have square roots, whenever you have polynomials, you can sort of compare the degrees. So it's not exactly the degree of the polynomial of the denominator, but at the denominator you have the square and then there is a square root. So it's something, it behaves something like a 1-degree polynomial. Okay, it's not exactly a 1-degree polynomial, but it behaves like a 1-degree polynomial. And on top you have a 2-degree polynomial. You have x and y. So it will converge faster, as in xy will converge to 0 and this will not converge to 0. And what is the exact factor that you have to determine, because you can compare square roots with individual quantities. I understand that this is not perhaps uh, if you want to know how to solve any problem, then this is not a good enough explanation. But then again there is no explanation that this is the function that you have to consider. You have to look at it and solve enough problems, and you'll train your intuition a bit better.
Okay.
And the functions that we give will not be very difficult to sandwich. So typically you will get something like, let's say, xy sine 1 by xy, something like this. Even this will not have a limit as you approach 0, right? But sine is always between -1 and 1. So you can just take this thing to be between minus xy. Okay, there's this sine guy over here, and plus xy. And this, goes to 0. So whenever there is a sign, you know that you can always uh, bound between two things, and then you can
Oh,
make it there. All right,
yeah.
fine. So limits
Thank.
and continuity we have taken up, and yeah, if there are other doubts, maybe we'll take it at the end.
Sure, sir. Yes, sir.
Okay, fine. Limits and continuity. While explaining all of these things, I did kind of give a recap, and then there's partial derivatives. So I will not write over and over again that it's a scalar valued multivariable function. Always assume that there's a scalar valued multivariable function in the background. So partial derivatives is it's either denoted by fxi or dou f by dou xi. The first principles definition is to take limit as h goes to 0 of x plus h ei being the standard vector. Yeah, because yeah, tilde, let's just use all of these things, divided by h. And if this limit exists, then we say that the ith partial derivative exists. And the generalization of this is that of a directional derivative, wherein you don't change the input variable only by, so this is a unit direction vector. You have this plus h u tilde. This u tilde. So in both of the things, what you're doing is you're measuring the rate of change as you change the input variable from x tilde to x plus a quantity which is in the direction that you're interested in. So even though this is the basic definition of partial derivatives, what is more useful, partial derivatives and directional derivatives, what is more useful for computations is for partial derivatives, for example, you fix all other variables and then differentiate with respect to the variable that you are interested in. That will give you the partial derivative. And for directional derivatives, under certain assumptions, you know that fu is nabla f dot with u. So what are the assumptions that need to be satisfied for this equation to hold?
It should be differentiable at that point, partially differentiable at all the axes.
It should be unit vector.
This is a unit vector. U is a unit vector. That's okay. But what are the conditions that are
Or
required on F?
partial derivatives at that point should exist.
That is
It should
not
be
enough.
it
They
should be
should exist
continuous.
yeah, partial derivatives should exist and continue. Works only when all partial derivatives existing is the same as saying the gradient exists and is continuous.
Only at that point, no, sir. You have
Yeah,
to.
yeah. So I've not written down the point, but if you're looking at a point, then you just need existence and continuity of the gradient at that point.
So basically, sir, in this case,
a piecewise function will never be possible in this case, right?
So if you have something like this,
Yes, yes.
at this point,
It's breaking
no.
continuity.
But if you have a nice enough, so what do you mean by piecewise function?
So basically, for a certain point, say for like it doesn't give the same value.
For things like this, you're saying,
Yes, yes, yes.
not always. If the gradient can still exist and it can still be continuous. I'll give you an example at the end.
Okay.
Or you have to check this condition. That condition is not automatically, it does not automatically fail for any piecewise function.
Okay, okay. Got it.
And
Got it.
f will be defined on the whole thing, and nabla f could still exist and it could still be continuous,
Okay, okay,
right?
okay. Okay. Okay,
I'll
we have
take
to
up
check.
examples at the end.
No problem, no problem.
Yeah. So this is one of the applications of the gradient. It is that if you take the dot product with any unit direction vector, what you get will be the directional derivative in that direction. That is application number one. So in week 10 content, we'll look at two more applications. One is the direction of steepest ascent. Ascent or descent. So to motivate it a little bit, what quantity does this signify? This is the rate of change of f in the direction u, right? Even if you go back to the first principles definition, you'll see that here I measure what happens to, like I take the ratio of, I can look at this as change in f in the direction of u divided by change in input, right? Change in, I'll just call it x tilde. So when I go from x tilde to x tilde plus hu, what is the change that happens? That is the numerator. And what is the measure of the change that has happened in the input? That is h. So fu is the rate of change of f in the direction of u. Now for every unit direction, I will get an fu if your function is well behaved, in the sense that its partial derivatives exist and are continuous. Let's assume that condition for now. So I'll call this condition as star for this lecture. So assume star. Now suppose I am on just one moment. Let's say I'm on a surface like this. Yeah, what is it about?
Sir, partial derivative is also a directional derivative in some sense.
Yes. So if
In
you
a
substitute
direction
u
like
is
this.
if you put u is equal to ei, you will get partial derivatives.
Sir, is this anyway in any way correlated with maximum minima in single variable calculus?
It will come in the week 11 content. Week 11 content probably. Yeah. This
Okay,
is one of the things. So whatever role your derivative plays in one variable calculus, in some sense, the gradient plays in multivariable calculus. So
got it.
you will
When you
see
say
that when we address it.
gradient function, sir.
Yes, gradient function is a vector valued function. So it's a vector with n variables. So in the case of one variable function, it would just be a vector with one variable, which is just a real number. So what does gradient measure? It measures the changes in each coordinate direction and puts it all together. Okay. Now, suppose I am at some point on this hill. This is something like, let's call it f. The graph of the function f of xy is equal to 2 minus x squared plus minus y squared. Let's just write just 1 minus x squared minus y squared. Now, as I'm on this point, I can take many directions, and the rate of change of f. What is f? F is just the height of this hill, right? The rate of change of f depends on the direction that I take. Suppose I travel in this direction. What is the rate of change of f?
Constant emerging.
y0.
F u of x.
Y is
No, it's not about
Oh,
y. xy is over here.
2x.
I'm saying if I travel along this circle, what is the change in f?
No change, sir.
I square. No.
It is
My
no
square.
change because
Okay.
the height is the same. No? So this
Yes,
height
sir.
is what is the
Yes,
value of
yes.
f. So the generic point on this is of the form x comma y comma f of xy. So the z coordinate, which is the height in this case, is f of xy. So I'm trying to say that this circle-like thing that I've drawn is at the same height. So if I travel in that direction, there is no change in f. So fu has to be 0. Maybe we'll take this example particularly. But if I travel in this direction, f is increasing, right? The height is increasing. If I travel in this direction also, the height is increasing, but it is not increasing as fast as what it would have been increasing if I travel along this direction. So at different directions, at a given point, if you take different directions, the rate of change of your f is different. Now I want to see what is the direction that I have to take for my function to rise fastest or come down fastest. So objective is to control fu. But what is fu? This, since we have assumed this, what is the expression for, let's say, a tilde is a point on our domain, which I'll call B. Okay, so how do I calculate fu of a tilde?
We'll
Gradient.
multiply the gradient function with the unit vector u.
Well,
With the
not multiply, but dot product.
dot product, sorry.
Yeah. But what is the dot product? How do I compute the dot product?
Multiply corresponding
In terms of the angle, can we rephrase it in terms of the angle?
cos theta is
Norm
equal
of
to dot
Norm of
product divided by norm of that, something like that, sir. I forgot.
So it will just be this.
Yes.
Where theta is the angle between the direction vector and the gradient vector.
Right, yes.
But what is this? This guy is 1. I've taken a unit direction. So what I have is just gradient of f at a, the norm of that, times cos theta. Now, if I want to maximize this quantity, if I want to find the u for which fu is maximum, what do I have to do?
Cos theta should be 1.
zero. Theta should be
Theta should
0.
be 0.
It should be 0.
Cos theta should be 1 or theta should be 0. Both are equivalent statements. And if I want it to be minimum,
Theta should be pi by 2.
Pi. It is pi.
it's pi.
Pi by 2. Okay.
You can go
Sir, why
negative
is
1.
it
No?
pi by 2? Why is it not pi by 2 will be 0? No? Oh, sorry. Negative.
And pi.
Sorry, sir.
You can have negative numbers. No?
Then
Sorry.
Yeah. So if you want fu to be equal to 0, then, well, all of these are depend on these. Now it is pi by 2. Now, if you want no change in f, then what is the direction that you have to travel to? You have to travel orthogonal to the gradient vector. So remember that theta was the angle between, theta is angle between u tilde and gradient of f at a tilde. So theta equal to 0 means that u tilde and the gradient is a vector. So that vector, the gradient vector and u tilde lie along the same direction. In other words, we have the following. Fu is maximum if u is equal to, let's all work with the point divided by. So why did this factor come in? Because I am considering unit direction vectors. So and it lies along the same direction. So what are the vectors which make an angle 0 with the gradient vector? They are positive scalar multiples of that vector. So throughout all this discussion, there is one subtle point that we have kind of overlooked, that what if norm of gradient is 0, or what if the gradient is 0? For now, just assume that the gradient is not 0. If the gradient is 0, then along every direction you have, it is what is called a critical point. We'll see later. But for non-critical points, you'll have that the direction in which f rises the fastest is this direction, which is the normalization of the gradient vector at that point.
Sir, how did you get this equation, sir? I did not understand.
So I want Fu maximum, maximum meaning theta is equal to 0. This we have established, right? So theta is the
Yes,
angle
yes.
between u tilde and gradient. So what does it mean to
Right.
say the angle between u tilde and gradient is 0? It is just that the u tilde is a scalar multiple of the gradient, positive
Right.
scalar multiple of the gradient. And what
Right.
is that multiple? That has to be such that, since we have assumed our u to be a unit vector, it is
Right.
forced to be 1 by its norm, so that this is a unit vector.
Oh, okay, sir.
So,
Got it.
so this forces u tilde is equal to c times gradient, where say c is a positive scalar. And then if you see norm of u tilde would just be modulus of c, which is c because we are assuming it's a positive thing. This proof you actually don't really need to see that directly, but norm of u is 1. So c is 1 by nabla f tilde if you want the complete proof. But you can just take this
Sir. Got
equation.
the motivation, sir. That's more than enough.
And what happens if, can you complete this then? Anyone?
Minus of
Minus of.
Yeah, here you need minus of, because the theta equal to pi means that it is a scalar multiple of gradient, but that scalar multiple is a negative number. And if the scalar multiple is a negative number, the only negative number which would make this a unit vector is minus 1 by the norm of the gradient. So maxima happens, so not maxima, but the direction of steepest ascent. So this thing is called direction of steepest ascent, and this thing is called direction of steepest descent. And this is equal to 0. Also, you can say that no change. Well, no change is not the precise way to say it. Like instantaneously, there's the derivative is 0 is all that you can say. But I'll just write it as it is. No change in f along u if nabla f dot u is equal to 0. I'm just rewriting this instead of saying theta is equal to pi by 2. Now, if theta is equal to 0 or 180, we can get nice expressions for what u tilde could be. But in general, you cannot get an expression for U just by an orthogonality property. It's a single vector, and your vector needs to be orthogonal to it. So you have many such vectors. So along any such vector, you will have that the f is stable in that direction, or fu at a tilde is 0 if the gradient is orthogonal to the direction, which is the same
Sir, in the
as, I mean,
sorry,
yeah,
sir,
go
in
ahead.
the diagram which you drew, when you're going perpendicular, the rate was fastest though.
No, so the gradient is this direction. What is the gradient? The gradient of this function would be minus 2x minus 2y, right?
Right.
So if I'm at some point, minus 2x minus 2y would be towards the origin.
So the gradient would be in R2, no, sir?
The gradient will be in R2. This is 2 minus 2x comma minus 2y. Sorry. Yeah. Nabla f at a point xy is minus 2x minus 2y. So what
Okay, sir.
is, if I'm at a point x comma y, this would be xy, right? This is the vector xy. So minus
Yes.
xy will be in this direction.
Right.
Okay.
Okay, sir.
Well, I can reshift it to make it uh, starting at the origin, but I'm just keeping it as it is because then if you look at the corresponding point over here, it says that you have to travel towards the image of the origin, which is up the hill. The direction of fastest ascent is up the hill, and fastest descent would be this. It is just the negative of that. And where there is no change, it is this. As you travel sideways along the hill. Your intuition and uh, the formula, they agree, right?
Yes, yes, sir.
Right. Even if you don't get the intuition, the important part to note is this. Right. This is called steepest ascent. This is called steepest descent, and this is a stable point. There is no change in f along that direction.
Sir, this is for
So which
all.
one is the descent
This is descent.
and
You
upper
want
one is steepest?
steepest ascent and steepest descent. Ascent
Okay, sir.
is increase in value and descent is decrease in value. You want the fastest increase of the value of f. So that is steepest ascent, and steepest descent is this.
Okay,
Sir,
sir.
this is for all values in the function, sir.
I didn't understand. Could you repeat?
So
What
for
you
every
mean
point
by
in the function, the steepest ascent will be gradient divided by mod of gradient.
the direction of steepest ascent will be, yeah, the gradient divided by the normalized gradient vector.
So it's for all points in the
Domain, yes, as long as your star is satisfied, which is the gradient exists and is continuous.
all right.
So the gradient is always pointing upwards. Is that the case?
Yes, in some sense, the gradient is the direction in which you will see a rise in the value of f.
So it just falls out of the way it is defined. Like we don't have to
Yeah,
worry about that.
as long as it's not 0,
Oh,
the gradient itself, if it is 0, so suppose you have something like this, and if you look at the gradient at the apex, you will see that it is 0. So there's no direction in which it increases. And there's no direction in which it decreases also by this formula, but actually you'll see that in every direction it decreases. So, but there is no way to measure in which it increases or decreases by this method. That's an equilibrium. Okay, so as long as your gradient is not 0 and the gradient exists and is continuous, you can say that the direction of steepest ascent is this, the direction of steepest descent is this, and the no change direction is this. Any vector which satisfies which is orthogonal to the gradient vector will be a point will be a direction in which no change is observed. instantaneously at that instant. Yeah.
Sir, ascent means an
So
increase in function.
increase in function value.
Oh, okay, sir. And that one descent is a decrease in function value.
Yes. In
Okay, sir.
general, ascent means increase and descent means decrease. Ascending, descending, it is just the same. Okay, so that's that. We'll take examples maybe later. We have taken sort of an example over here where we have done the calculations. More examples, I'll do it in this later or maybe in the next session. So my plan is to hopefully complete at least 3 out of 4 topics in this session so that we can take more problems. And I want to do a session on visualizing all of these things using GeoGebra or something, because you have R2 to R functions. If you don't visualize, then you're not doing justice to the circuit. You
Yes.
guys could do it by yourselves, but if we have time, we'll take that up.
Sure, sir.
The next thing that the derivative allows us to do is compute tangent lines and tangent hyperplanes. So before I go to that, this direction of steepest is this point. For one variable function, f prime x, okay, I'll just draw a diagram and not do all the theory. So if I have some function, so this is, let's say, y is equal to f of x. So what is the tangent line to this? This is a tangent line
The
at this point, right?
derivative at that point.
The tangent
The
line is
slope
not the
is,
derivative.
sorry,
Yeah,
sir, the
yeah,
slope is the
Slope.
derivative.
Slope.
yeah. Okay. So what is this point? So
Tangent.
suppose I have this point has x coordinate x naught, then y coordinate would be,
F dash x. Oh, sorry.
this
F
is
of
f of
x.
x.
F of
So
x.
x
Yes.
f x is the
Sorry,
uh,
sorry. Yes, sir. Yes, sir.
any point on the graph is of the form x comma f of x, right? So if my x
Yes, sir.
coordinate is
Yes.
x naught, my y coordinate is f of x. That is what it means to say the graph of the function. And since I know that x naught
Slope
comma f
is,
of x
sorry.
naught and m is equal to f prime x naught, right? The slope of the line is this. So I can calculate the tangent equation of the tangent line, which is y minus f of x naught. So this is from y minus y0 is equal to m times x minus x0. So if you have the slope at one point, you can compute the equation of the line as follows. So I can just write this as f prime x naught times x minus x naught, right? So what allows me to do this is the slope of this line that I know. As soon as I know the slope of the line, I get something called the tangent line. Let us keep this equation over here in mind, and let's try to do the same thing for a multivariable function. So for visualization, it is only possible to do two variable functions. So let's again take something like that hill that I want to draw. Right? So something like this. So consider some point over here. What would be a tangent line? Like what would a tangent line look like? This is a surface, right?
A plane, I guess, sir. A plane.
A tangent line still exists. No, like this is a tangent line. And something like this would also be a tangent line. Like just imagine that this is tangent, but in some other direction. So suppose,
Yes.
if for simplicity, let's just use the apex of the hill. So there things will be easy to, right? So this is also a tangent, This is also a tangent. This is also a tangent. So in general, you will get a tangent plane, which is to this point. You have a plane which is tangent to. Instead of a line, in the two-dimensional case, you have a plane which is tangent to. First, we'll see how to get these individual lines. I'm not going to give the proof. I'll just give you the formula and a way to see why that thing happens. If you look at any point on this plane which passes through that point, that will be a tangent line, correct? So you
Sir,
have,
could you please repeat that statement?
okay, do you understand what this tangent plane is? What this plane is that I've
Yes,
drawn?
yes, sir. Yes, sir. Yes, sir.
So this is just a straight, something parallel to the z-axis that rests on top of the apex of the hill.
Yes, sir.
And now if I consider within, so this is an infinite plane. I've just drawn a part of it. So if I consider any line in that plane that passes through this point, try to visualize this. Those will be tangent lines to the graph, right?
Yes, sir.
So we want to get to know what the equation of such lines are. So at a given point, there are infinitely many such lines because there are infinitely many directions, correct?
Yes, sir.
Right. But in this case, in the one-dimensional case, there was just one tangent line, and this is what we wrote it as.
Yes, sir.
Now, what is an interpretation of a line in R2? In terms of the linear algebra that you have already learned in the past few weeks, what are lines?
Dimension of 1, if I'm correct.
Are they subspaces?
Yes, sir. If they pass to the origin, they're definitely subspaces.
Yes. But in this case, do they pass through the origin?
No, sir.
No,
Not necessarily.
no.
So in that case, what happens? Lines which do not pass through the origins are a
Affine
special kind of.
subspaces, sir.
So the tangent line is an affine subspace, correct?
Yes, sir.
So I can describe this line. Let me call this line as L. And this is an equation for L using the coordinate geometry that we know. But L can be written as some vector or some point plus some subspace, because it's an affine subspace. An affine subspace is just translation of a vector subspace. So what is this V naught? What choices do we have for V naught?
The V
It is
naught,
not
I think
unique,
we'll
right?
take. Yes, sir. It's not unique. Anything that passes through the affine subspace, we can take V naught.
Yeah, so we have one such thing, right? We
Which
know
is that
the
point?
description. Yeah, we know that x comma fx naught, x naught comma fx naught. This passes through the affine subspace that we want to define. And what would you,
Right.
how would you describe the vector subspace, the corresponding vector subspace? It's a one-dimensional subspace. This is a one-dimensional affine subspace, so its corresponding vector subspace is one-dimensional. So it is t times some vector. What's a one-dimensional subspace? It is just t times some vector. No? So if you take all of these things, then you'll get a one-dimensional subspace. I should not use this again. I'll use some tu naught. Is this not a one-dimensional subspace?
It is.
And all one-dimensional subspaces are of this form?
Yes, sir.
Yeah.
They should be.
So I want a vector which I can use as a representative for all the vectors in that subspace. So that vector can be this velocity vector. Right? I know the velocity at that point. The velocity vector at that point is actually 1, m. But that m is actually f prime x naught. So if you're not understanding all the steps that are happening over here, it's fine. I'm just giving you an idea of what motivates this. Maybe if we have time at the end, I don't know how many things we're going to do at the end, but okay, let me just.
Sir,
Yeah.
yeah, so basically this U, like, which is the vector space basically.
Mm-hmm.
So this is basically x comma mx only, right?
This is x comma mx. Yes, that's the slope. No, so it's x comma mx.
Yeah, yeah, yeah.
So it's
Okay.
x times 1 comma m. So the vector that you can choose for as the representative for that vector subspace could just be 1 comma m. This
Understood.
can be written x comma mx can be written as a span of 1 comma m,
101 comma m. Okay.
and m is f prime x naught by definition. So this is a subspace, by the way. As you vary t, you will get different values. So this is a particular vector plus a subspace. So this is the affine subspace representation of the tangent line in one-dimensional vector calculus. We'll do something similar. I'll first give you the expression for the line. Once again, a tangent line would be something plus a one-dimensional subspace, which is t times something. Is that fine?
Yes, sir.
So what would this be? So suppose this is the graph of a function. Suppose this is the graph of f of xy, and my particular point over here that I'm considering is x naught y. So if I want to give the description of an affine subspace in R3, I should give it as a point in R3 which lies in the affine subspace plus t times some spanning vector for the corresponding vector subspace. Do we have the point for the vector subspace? The point for the affine subspace?
Yes, sir. X naught comma y naught comma f of x y x naught y naught.
Yes. So if I can take the particular point that my affine subspace passes through to be x naught y naught, fx naught y naught. In this case, what would be the direction? What would be the slope of in some sense, slope? That would, of course, depend on what direction we choose, right? It's not just 1 comma m as it was over here. There are different slopes as if you take tangent lines of different directions. So it turns out that I'm not going to give more. I'm not going to say more about this. In the props videos, he has explained it a little bit more. I'm just going to give the expression. The vector which spans the tangent line at the point is u1, u2, where u is a direction vector. So if you take different direction vectors, you'll get different tangent lines. So for the direction u1, u2, which is u tilde, the vector u1, u2, fu at x naught y naught. This is the vector which spans the one-dimensional vector subspace corresponding to this affine subspace. So this is the equation, or I should not say equation, expression for the tangent line at x naught y naught in the direction u is equal to, I will take equivalent direction. The unit direction u1, u2. So just to summarize once again, in the one-dimensional case, you will just have one tangent line. But in this case, you will have a tangent line for each direction, as we were expecting, because here you have multiple tangent lines. So you can choose which direction to go along, and you will get a tangent line in that direction. So it is not enough to just say what is the tangent at this point. It has to be specified what direction you're considering as well. So the right thing to look at is what is the expression of the tangent line at a given point in a given direction. So you need two things, a point and a unit direction. If that is given, then this is the expression of the tangent line that you want to compute. So what is this t? So what are the points on this tangent line? So points on the tangent line.
Sir, sorry to interrupt. So this u equal to u1, u2 is basically the unit vector, right?
Yeah, the unit direction along which you want to look at the.
Understood. Understood.
So does it have to be a unit vector or can it be a normal vector and we have to normalize it?
It has to be like if you're given non-unit vector, you have to normalize it, and because when you're doing this,
Got it, sir.
typically you use the
Unit vector.
gradient.
Got it,
Yeah.
sir. Thank you.
This would just be f of x naught y naught times x naught x naught. So as you vary t, you get different points on the tangent line. So let's take up an example. That same example, but I'll just demonstrate to you that how this equation works. What was 1 minus x square minus y square? It was exactly the same thing. It is the inverted paraboloid shifted up by 1 unit. So this is in R3. So this is your domain xy. XY plane is your domain, and z is the height. So z is equal to 1 minus x square minus y square. So let's look at all the tangent lines at the apex. What is the apex of this paraboloid?
1 comma 0 comma 0. Sorry, 0 comma 0 comma 1.
0 comma 0 comma 1 is the uh, coordinates of the peak. So I want tangent lines at 0 comma 0. Right. So we talk about tangent lines in reference to the domain values. So at 0 comma 0 means 0 comma 0 comma f of 0 0, which is 1. So what does the formula say? It says that x naught y naught f of x naught y naught plus t times u1 u2. Now u1 u2 is not specified. I would like to vary all u1 and u2 and find this fu of x naught y naught. Now x naught y naught is given. What is f of x naught y naught? That we can compute. This will be 0 0 1, and u1 u2 is not given. But what is the general expression for fu of x naught y naught?
The directional gradient
So x naught
into
y naught
dot.
is 0 0 over here.
I think it's
Gradient
0,
at 0,
sir. It's 0.
times the direction.
Nabla f at 0 0 dot
Dot product
u1 u2.
u1.
But what is Nabla f?
Minus 2x minus
0 comma 0.
2x minus 2y.
This is at 0 0. Remember, dot with u1 u2. but this happens to be 0, 0 dot u1, u2, and this is just 0. Here, I did not have to worry about whether the function, that the gradient exists and is continuous, and whether I can use this formula, because this is a well-behaved function. It's polynomial function, so that is well behaved. So here all of those things are satisfied, but in general you might want to look out for that. But anyway, fu of 0, 0 is 0 irrespective of what u1 and u2 I consider. So if I rewrite this, what will I get? I'll get 0, 0, 1 plus t times u1, u2, 0. So the points on the tangent line are of the form tu1, tu2, comma 1. As you vary t, you will get different values. So suppose I take u1, u2, let's just do some things. For u1, u2 is equal to, let's say 1, 0. The tangent line is t, 0, 1, t implied. So the tangent line is always a one parameter family, right? It has to have as many vectors as many points as there are real. So this is the tangent line is t01. What does the line t01 look like? The y value is always 0. The x value is varying. The x value is varying. The y value is always 0. The z value is always 1. So it's a line like this. You see, it's parallel to
X.
it's like the x-axis just shifted upwards.
So
You
can
see
you,
that this is the tangent line? Just one moment. Okay. This is t01.
so
Only
can,
x is changing.
so can you
Y
explain
and
this?
z are, I'm explaining.
Okay.
So what does changing in y would mean? It would go this way or this way. That is change in y, right? So this is, what is y is equal to 0? Y is equal to 0 is the xz plane.
Yes, sir.
And z is equal to 1 is the shifted xy plane. Xy plane parallel of a parallel of xy plane at z is equal to 1. Right? So I want both of these to be satisfied. So it will be the intersection of both of them. And that is exactly this line. So
So
this
yes,
line
sir.
is just move the x-axis to this point.
So we can say this is an affine space of the subspace that spans 1, 0, 0.
Yes, correct. That you can see also. This t01, you can write it as t00 plus 001.
Plus 0, 0, 1. And t is a span. So span of 1, 0.
T is a variable, so it corresponds to span of 100.
Yes, sir.
Can you explain this part once again, sir?
The visualization of T01.
Yeah, from this part, sir. 001 plus T1 U2 0. Yeah.
So applying the formula to get this part is clear, right?
01 plus T1 U2 0.
If it is not, then we'll see that as well. Is it clear?
So just one question. Will it always
Just
will that yes, sorry, sir.
Okay, T1. Okay. This part is fine, sir. The tangent line. So this 001, this we are considering this part, like just have some confusion
So
in.
the equation of the line.
Okay.
You need two things.
Okay.
You need this point, which is given by x0, y0, f of x0, y0, plus t times moving in that direction.
Okay,
U1,
x2 y
U2,
naught is 0,
and
0.
derivative. X
Got
naught,
it.
Y naught is 0, 0. So you will
Okay.
have 0, 0, 1.
And
That
okay.
is your first part of the equation. And t times u1, u2, 0. Irrespective of what u1 and u2 are, we prove that the directional derivative in the direction of u is 0.
Okay. Correct.
Okay, so it's in general it is tu1, tu2, 1.
Okay.
But
Okay,
then I
fine.
considered the particular case where u1, u2 is equal to 1, 0, which gave me this thing, t0, 1, where t varies in r.
Yeah, okay. Okay. So this you
Now
have
if I
assumed
go,
for U1,
I'm
U2.
just looking. Yeah. U1, U2 was not given. So if these are equations of all possible tangent lines, so by varying U1, U2, you will get all possible
Okay,
tangent
we will
lines.
get many tangent lines like this. Okay,
Yeah,
okay.
yeah. So what is the tangent line T01? So 001 is just the apex, and then you have 101, which will be over here, which is in the XZ plane. Just imagine that 201, 301. It will all lie along the same thing. So it will be something like this.
It will be parallel to the x-axis. Okay, something like that.
It will be parallel to the x-axis and in the XZ plane at height 1. Z is equal to 1.
Z equal to 1. Okay.
Because that is what is forced, right? You have no choice for y and z. Y is equal to 0 has to happen. Z is equal to 1 has to happen. So it is the intersection of the XZ plane and the plane Z is equal to 1, which is exactly this line. You have this
Yeah, y equal to 0 is the exact plane. Correct.
XZ plane, and then you have this thing like this. So the intersection is this line. That's not a good diagram, but fine. I hope you understand.
Yeah, got it.
T01, you can actually go to GeoGebra or something and just type in T01 and you will find this line. It will automatically assume it to be a
Sir, I hope in the next
variable, and
you would be doing a bit
yes,
on
in the
the visualization part,
yes,
right?
yes,
Then it should be
I
clear.
will. I want to do one session on that.
Yeah.
That's why I'm not taking many examples over
No,
here.
no problem. No problem.
What happens if u1, u2 is 0, 1? I'll get another tangent line, but the tangent line in this case, can someone give me the expression for the tangent line?
0T1.
And can you explain what that is?
Line, I think same thing, but it'll be parallel to y-axis. Sorry, the
0T1.
xy plane. Sorry, sir. It'll be parallel to the. It'll be. You shift it 90 degrees, sir. So kind
Yeah,
of like that.
it's like this. So it has to pass through this line. So ah, hope this is better. How? No. Okay, good enough. So it is this line, which is translating the y-axis using the vector 0, 0, 1. That's what is happening over here, right? It is 0T0 plus 0, 0, 1. So in general, what you will get is what you have to notice is this third vector, third coordinate of any tangent line is constant 1, irrespective of what I choose for my u1 and u2. So it will be in the plane z is equal to 1. Right?
This will be
What
in
is
the
the plane z is
YZ
equal to?
plane, right, sir?
This one will be in the YZ plane. Yeah, the second one will be in the YZ plane. In general, every tangent vector will be in the plane z is equal to 1. And that is expected, no? Because we are looking at all possible tangents at the peak of the hill. So that has to be the flat thing. That has to be a copy of, that has to be exactly z is equal to 1. Do you see that?
Sir, geometrically, I understood, sir, but how will you derive it algebraically, sir?
So here you have this, right? It has to be z is equal to 1. It has to, I mean, every point, every tangent line in this should be in z is equal to 1. That at least one part is there. And we'll see the tangent hyperplane in that is the next concept.
All right, sir. Thank you.
Okay. So for the same thing, for the same function, just to demonstrate a better example, for f is above, compute this example actually. Tangent line at some other point. Let's take some other point. Something like 1, 1 in the direction. Let's say 1 by root 2, 1 by root. Maybe just put minus.
Sir, could you generalize it, sir? Then it will be maybe more clear for me.
Generalize
U1,
what?
U2. Sir, the direction, could you use it as U1, U2? And then substitute?
No, I want to give one particular example because that may be a bit too abstract. Like if I start out with
Sure, sir.
the
No problem,
abstract
sir.
thing and then I substitute, that will be. This is more direct.
Sure, sir.
So
No
I
problem.
want to do one direct example as well. So you
No
know that
problem.
f of xy is 1 minus x square minus y square. So what is the point under consideration? That is x naught, y naught is 1, 1. And f of x naught, y naught. What is f of x naught, y naught in this case?
-1.
Minus 1. u1, u2 is given to be 1 by root 2, 1 by root 2.
Minus 1.
Minus 1 by root 2. So what is fu at 1, 1?
For that not gradient.
The gradient is minus 2x minus 2y, right? I'm skipping a few steps, but this would be minus
-2, -2.
minus 2 minus 2 dot 1 by root 2
Minus 1
minus
by
1 by
root.
root 2. And what is this? Oh, this is actually 0.
Yes, sir.
Yes, sir.
Fine. For non-zero things also the computation is similar. So equation of the tangent line with this data, what would that be? 1, 1, minus 1 plus t times 1 by root 2 minus 1 by root 2, 0. So you can leave it at this, or you can say that x is equal to 1 plus t by root 2, y is equal to 1 minus t by root 2, z is equal to.
-1.
Okay, I just changed some of the data. I want that z to be also dependent on this thing. So I'll change the unit direction to be 1 by root 2, 1 by root 2 itself. So u1, u2 is 1 by root 2, 1 by root 2. So this will be 1 by root 2, 1 by root 2. And here what will I get? Minus 2 root 2.
Minus 2 root 2. Yes.
I've changed the only change that I've made is I've considered in the direction 1 by root 2, 1 by root 2 itself. So corresponding things will change. And I'll get the pointers minus 1 minus 2t root 2 root 2t, whatever.
So you have considered 1 by root 2, 1 by root 2, right?
Yeah, I just changed it afterwards because I don't want that directional derivative in that direction to be identically 0. So this is the equation. This is also called parametric equation. You say x, you write x in terms of t, y in terms of t, z in terms of t. There is another symmetric version, the ratio version. So let's leave it at this itself for now. For me, this is most natural because this looks like an affine subspace, right? It's a point plus a vector subspace. Now,
So, sir, how you got
yeah,
that -2, sir? Fu of 1 comma 1 equal to -2 into 1 by root 2 comma 1 by root 2.
so this is gradient of it.
So that you calculated in the previous sum, right?
Yeah, it is minus 2x minus 2y, no? So
Okay.
this is gradient f is minus fx minus fy.
Okay, okay,
Sorry, fx fy,
okay,
which is in this case minus 2x and minus 2y.
okay, sir. Okay, sir.
And I just substitute. That's why I said I'm skipping a few steps over here, but calculating gradient should not be a big problem. So then I took the dot product with the direction vector to get 2 root 2. So if, let's say, 2BC is a point on the tangent line, find B and C. Can you guys do this?
Yes, sir. No, sir. Could you please explain, sir?
No, sir,
So
we
you
can
have
find
the
it.
equation.
Yes, sir.
We
We
can
have to substitute 2x as 2 and then t we will get.
Yeah,
And
you
then
can.
we'll.
Yeah, please take 2 minutes and do it and let me know what the answer is.
Y is 0 and Z is -5.
So y is, so b is
V0.
B is 0 and C is -5.
C is minus 5.
minus 5, is it? Yeah, this is correct. Does everyone know how we got here?
So I could
Yes,
get
sir.
the value of t as root 2, but after that I'm not able to proceed.
So the points of the tangent line are of the form 1 plus t by root 2, 1 minus t by root 2, and minus 1 minus 2 root t, 2 root 2 t. So if I say that this is equal to 2, this would imply that t is equal to 2,
Root 2,
as you said. So what would this become?
0.
Yeah.
1 minus root 2 by root 2. 1 minus 1, 0.
So this has to be
So how
0.
does that relate to b, sir? That's what the point is.
No, so 2 comma b comma c is a point on the tangent line. So
Mm-hmm.
points on the tangent line are of the form 1 plus t by root 2, 1
Okay,
minus t
okay,
by root
okay.
2,
Got it.
minus 1 minus 2 root 2
Yes,
t.
sir. Yes, yes.
So if I know that the first coordinate is 2, that corresponds to some parameter value t. And corresponding to that parameter value t, what are the y coordinates and the z coordinates? This is what the question asks. Did you understand? Did everyone get it?
Basically, it is trying to say that the points that will satisfy that equation.
The points that you obtain by varying t along real numbers will give you all points which lie on the tangent line.
Yeah.
Now,
So
if
it
2
has to
comma b
satisfy
comma
the
c is a
equation of
point,
tangent.
there is no equation that it needs to satisfy. It has to be a point of this form. Okay,
Yeah.
if you're
Yes,
saying
sir.
that 2 comma b comma c is equal to 1 plus t by root 2, 1 minus t by root 2,
Yes, sir.
minus 1 minus 2 root 2 t.
Yes.
If this equation has to be satisfied for some
Yes.
t.
Yes. Got it, sir.
So, for example, if I go back to this example and look at this, and I say that can a point of the form x y comma 2 be on any tangent line? That is impossible, because even if I vary t, I cannot change this third coordinate, right?
Yes, sir.
Yeah. So all tangent lines lie in the plane z is equal to 1. So this will never be part of any tangent line. This x comma y comma 2 will never be part of any tangent line. All right. So these are some problems from tangent line. So the thing to remember is tangent line. Okay, after tangent plane, I will write both of them together. So next equation of tangent plane. I'll give a short uh, derivation of the equation of the tangent plane. So where have I given the expression? Right. Here, I'll just mention over here that the same formula is valid in higher dimensions as well. Just because I was using this example does not mean that it would not hold in other things. In higher dimensions, we don't have this visualization, but the point still remains the same. It can be described as an affine subspace which passes through the point x tilde comma f of x tilde, and the corresponding vector subspace is u tilde comma fu. Fu is a scalar. The directional derivative is a scalar. So this is in Rn plus 1. Wherever this f is a function from Rn to R, then this is a line in Rn plus 1. All right. So the same thing holds. The first, this here, your first n coordinates will be x1 up to xn, the point that you're considering, and the last coordinate will be the function value at that point. And this directional derivative will take up, unit directional derivative will take up n spots, and the last coordinate will be the directional derivative in that direction. So that's the general formula. Now let's go to the tangent plane. Once again, tangent plane, I'll explain using R2 to R, but essentially the same equation holds in higher dimensions. Let's take help of this itself. We saw that all tangent lines at the apex have this property that they lie in the plane z is equal to 1. So what I'm interested in is I take all possible directions at this point and look at all possible tangent lines and put them all together. And that happens to form a plane when you have that assumption star that we described earlier, that the gradient exists and is continuous at every point. Partial derivatives exist and continuous. This would imply that the tangent plane exists at that point. And what is the equation of the tangent plane? So to get the equation of a plane in R2, what are the things that you require? You can describe it as an affine flat, but I'll do something different. I want to write it in terms of ax plus by plus cz is equal to b. So just like for the equation of a line in R2, you have, if you have a point and a slope, you can write the equation of a line. If you have 2 points that the line passes through, you can write a line. How do you write the equation of a plane? What would be sufficient to write the equation of a plane?
Any line in that plane?
But if you have only one line, there are many planes that pass through it. There's this plane, there's this plane.
We need 2 points, sir. Or 3
So
points, sorry, 3 points.
Two
Yeah.
lines.
3 points would be sufficient. But 1 point and normal vector is also sufficient. Do you guys see it?
Yes, sir. Yes, sir. But that point should not be on the normal vector, if I'm correct.
No. A vector, you can start from that point also. So if I just have a vector, the planes that are orthogonal to it or planes that are perpendicular to it, there are infinitely many of them.
Yes, sir.
And there will be precisely one on which this point lies.
Oh, okay, sir. Got it, sir. Yes, sir. Makes sense.
Right?
Got
So
it.
if for example, if I take the z-axis, the planes that are perpendicular to the z-axis are parallel copies of the xy plane. And given any point, it will be exactly on one such plane.
Right. Yes, sir.
And you can check this. This is a coordinate geometry equation of a plane through x naught, y naught, z naught, and perpendicular to ABC is a times x minus x naught plus b times y minus y naught plus c times z minus z is equal to 0. This is a standard result in coordinate geometry. You can go back and check this also if you want. Now, coming back to the context of our tangent lines, tangent equations, whenever we are talking about tangent plane to the graph, if I look at to the graph of f at, let me say, x naught, y naught, f of x naught, y naught. So the point on the graph would be something like this, right? X naught, y naught, f of x naught, y naught. So we have a point, x naught, y naught, f of x naught, y naught. So in order to find the equation of the plane, what do we require? Using this, if we want to do that. What is the only thing that is missing?
Sir, that
Okay.
vector, that perpendicular vector.
Exactly. So if I know a point and a perpendicular vector, I can get the equation. I know a point, x naught, y naught, f of x naught, y naught is the point through which the plane passes. So that I know. Now I want a normal vector. How do I calculate this normal vector? Any normal vector will do. So
So what is this capital
There'll
A,
be only
capital B, and capital C?
this is they come from the perpendicular. A comma B comma C is perpendicular to the plane. X naught, y naught, z naught passes through the plane. Then
Okay.
this is the equation
It's
of the.
also a point which is perpendicular to our plane. The plane
It's
which
a vector which is ABC is a vector perpendicular to the plane.
Okay.
So when you say vector, it means it's starting at the origin and ending at ABC, right? So just to
Yes, or any or any parallel translate of that. So we don't distinguish vectors with the same.
But in vector algebra, they clearly told that it's always starting from origin itself.
Yes. If you want to find out the value of that, but in some places you will need it to be. But in this case, yeah, you can assume that it starts from the origin and ends at ABC.
All right, so thank you, sir.
Yeah. So we know that we want this tangent plane and we want the normal to the tangent plane. In order to compute the normal to the tangent plane, what we will do is we will take two lines in the plane. So every tangent line in the plane will also be orthogonal to the normal vector, right? Let ABC be a vector perpendicular to the plane, to the tangent plane. Now, what is the tangent plane by definition? The tangent plane is the collection of all
lines.
Tangent lines
at a point.
So ABC is orthogonal to I'll just write this U1, U2, FU at that point, FU at x naught, y naught. Remember that this is the vector which is along the direction of the tangent line. This is what we scale and shift by so as to get this tangent line. This is the second part of the tangent line equation. And this is the vector which gives you the direction of the tangent line.
Right. Yes, sir.
So this vector and this vector, they have to be orthogonal to each other. So in this case, we kind of look at u1, u2, fu1, u2 as this vector, even though it might not start at the origin. Here, those vectors are essentially the same. But okay, this is a fact that ABC has to be orthogonal to each of the tangent line, which in turn means that it has to be orthogonal to every u. For every u, u1, u2, fu, x0, y0. Now, what are the two special u1, u2s that we know?
0, 1, 1.
E1 and E2.
Yeah. So if I take 1, 0, what is f10? What is the special name for that?
X-axis.
It is fx. It's a
Oh,
partial
sorry.
derivative with respect to x.
Sorry.
The directional derivative in the direction of 1, 0 is just the partial derivative.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
So if this is orthogonal to this, what does this imply? What is the definition?
Then it will be a translation of the x. So
I'm just saying,
one of
just
the
use the
planes, YZ
dot
plane.
product formula.
Oh, sorry, sir. Yes, sir.
Is this not correct?
Yes,
Correct, sir. Correct,
dot
sir.
product has to be there.
Similarly, I can take this vector and I need my ABC to be orthogonal to this vector as well. Right? And what does this give me?
B plus C
B
C
plus
B
C
B plus C
is
F
equal
Y.
to 0. Fy is equal to 0.
Right? So I can write everything in terms of C. So the normal vector is of the form minus C fx. I'm not going to write the it's not y not part. Minus C fy and C. What have I done? A is equal to minus C times fx is what I've done over here. B is equal to minus C times fy is what I've done over here. So the normal vector to the plane will be of this form. Is that fine?
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
The normal vector I assume to be ABC, and using the properties that it has to be normal to all tangent lines, in particular to the tangent line corresponding to the direction 1, 0 and 0, 1, I got two equations. And using that, instead of ABC, I wrote it as minus C times fx minus C times fy, comma C. All of this at x0, y0. I'm not writing x0, y0 over and over again. Is that fine?
How did you get C?
Sorry?
How you get C as Z?
Unit
So A,
vector.
B, C is the okay. How do I deduce what C is? I can take anything
Yes,
to
sir.
be C as long as it's non-zero, because if some vector is normal vector, then any multiple of that will also be a normal vector, right?
Yes, sir. Yes.
So normal vector can be described up to scaling. So I'll just take C is equal to 1 for convenience. So what we'll get is minus fx minus fy 1 is a normal vector to the plane. So now that we have a normal vector and a point on the plane, we can compute the equation, right? Now I'll rewrite this x naught y naught so that there is no confusion. X minus x naught minus fy times fy of x naught y naught times y minus y naught plus z minus z naught. So what was this? This was just using this equation and substituting a, b, and c. A was minus fx, b was minus fy, and c was 1. So this is the equation of the plane. Oh, but z0 is just f of x naught y. The point is x naught y naught fx naught f of x naught y.
So
So
this
you
is
can write this as,
of the tangent plane, right?
yeah, this is the equation of the tangent plane through the point x naught y naught, or at the point x naught y naught, which is through the point x naught y naught fx naught y. So to make this slightly easier to read, you can write this as nabla f at x naught y naught dot product with this vector x naught y naught minus x naught x minus x naught y minus y. Is that clear? Is it clear what happened from here to here?
No, sir. Can you explain it?
Yeah, z I've kept it on the same side. Fx naught y naught I brought it to this side, and these other terms also I brought to this side. But I wrote that as gradient at x naught y naught dot product with x minus x naught y minus y naught. What is gradient dot product with x minus x naught y minus y naught? So gradient was just fx comma fy dot with x naught y x minus x naught y minus y naught will give you exactly that fx times x naught minus x, sorry, fx times x minus x naught plus fy times y minus y naught. It's just
Sir, can you
compactified.
Sir, can you
Yeah.
explain from below the c is equal to 1 for convenience after you got that equation? The last two lines.
Okay. C, I can take anything so long as this thing does not become 0. So
Yes.
I can take C is equal to 1. I took C is equal to 1. So now I have all the pieces of the data that I need to find the equation of the plane. If you
Right, sir.
remember, I wanted a point and a normal vector. Now I have the point
Right, sir.
x naught y naught f of x naught y naught and the normal vector minus fx minus fy 1. So
Oh, you just substituted in the formula. Okay, sir. Got it.
yep,
Sir,
yes.
okay,
Just
okay,
one
okay.
minute. This is a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. So c is 1, b is minus fy, a is minus fx. And then I rearranged to make it
So you have basically converted this into a dot product form, right?
yeah.
Okay.
Instead of writing fx times x minus x naught,
So, sir, essentially
it is
the last two lines both are same, no, sir? Last two
yeah.
lines.
It's just rearranging and simplifying.
Okay, sir. Got it.
So if you have a1 b1 plus a2 b2, I've just written it as dot product of. So this you remember, this is just fx comma fy at the given point, but that I've written as gradient. So what is the advantage of writing it in this form, or why did I do all these simplifications in this manner? Is let's go back to the one variable thing. The equation of the line is of the form y is equal to, I'm just going to rewrite it, plus f prime x naught times x minus x naught. Now compare that with the equation of the plane. In this case, the role of y will be taken up by z, which is the variable corresponding to the function value, and the domain things like this. So this is nabla f, but this is a vector, so I cannot really multiply, but I will do a dot product. So one easy way to remember the formula is this: a direct generalization of the one variable case, where instead of f prime x, we use gradient. So this is why gradient is somewhat of an analog of the derivative of a function. Wherever you have derivative of the one variable function, you can expect there to be some corresponding notion with the use of the gradient. And you can just multiply these two real numbers, but here you cannot multiply vectors. You have to take the dot product. So that is one way to, even if you forget the formula, to just quickly go back to the one variable case, put nabla f wherever there is f prime, and you'll get it back.
Sir, so essentially the last equation is the tangent plane passing to a certain point
Yes,
on the surface. That's it.
yes. So yeah, so let's write that down. Let z is equal to f of xy be the graph of a function satisfying star. The star is way back, it was said what star was. So z is equal to f is the graph, f of x is the graph of a function. There are two things: tangent line at x naught, y naught in the direction u1, u2. That would be given by the set of all, I mean, the set vary with p varying in r x naught, y naught, f of x naught, y naught plus p times u1, u2, fu x naught, y naught, p in r. So for the tangent line, you need a point and a direction. But for the tangent space, you don't. Okay. Tangent plane, you just need a point. And that would be given by z is equal to f of x naught, y naught plus gradient of f at x naught, y naught times this vector x minus x naught, y minus y. And the same formula holds for higher dimensions as well, with obvious changes. So here you will have x tilde. So I'll just write it separately over here, but it is not much different. For higher dimensions, you'll have line. I'm not going to write the whole thing. X tilde, f of x tilde plus t times u tilde, f u tilde, x tilde. And there you will not have a plane, you will have something called a hyperplane. Hyperplane means a plane which is of dimension 1 less than the space it is in. So you saw that in R2, when we are looking at functions of this form, you'll get a line. So that is of dimension 1 less than the space it is in. So it is of dimension 1 in the space of dimension 2. In R3, we saw that what you get is a plane. So it is a space of dimension 2 in a space of dimension 3. So similarly, when you're looking at higher variable functions, you will be working in the space Rn plus 1, and the plane that you will get will be of n dimensions. So, and that equation will be given by f of x tilde plus gradient of f at x tilde dot product with, it's like, uh, uh, I'll just write it as, it's like, this is a particular one now. How do I write this? I just write this as, this is the last variable xn. I just write this x naught tilde. So this will be x1 minus x naught 1. There should be a better way to write this, but hopefully this is not. You understand, right? It's a, the first one is a variable and the last one is xn plus 1. Sorry, xn minus x0. It's just like x minus x naught, y minus y naught. You'll have x minus x naught, y minus z naught. If you're in 3-variable case or in higher variable, you'll have x1 minus x naught 1. Like for the particular, you'll subtract a variable from a particular.
Yes, sir.
Yeah.
You can write it as
Yeah.
still minus x naught till n.
Yeah. That you can. So
Still
now it will
minus
be
x naught
x
till
tilde
n.
minus x naught tilde. Yeah, that's it.
Sir, in the hyperplane, why did you write xn plus 1?
So if you have a function of, let's say, one variable, then you will have x2 is equal to x1. It's actually y and x, but I'm just writing this as so that it is you can see what's happening. X1. Okay. Let me
Okay,
not
sir. Got it,
complicate
sir.
things.
Got it, sir.
You got it, right?
Got it, sir.
So when you have a function of one variable to one variable, your graph is in
The output.
in two variables.
Yes, sir. Yes, sir. Yes, sir. The graph is in
So
two variables. Yes, sir.
yeah. So when you have a function from R2 to R, the graph is in R3.
Yes, sir.
When you have a function from Rn to R, the graph is in Rn plus 1. So your last variable will be n plus 1, and your input variables will go only up to n.
Okay, sir. So suppose if, sir, here, what is n again? Could you please?
And okay, so this is higher dimensions. F is from Rn to R.
Okay, sir. Got it. But, sir, x will only come, it'll be only x1, x2, x3, xn. How will we get xn plus 1?
The hyperplane lies in n plus 1 space.
Oh, okay, sir. So z, so for example, in R2, yes, sir. Kind of got it, sir. Got it.
Yeah, so you have a function f of xy, which is x square plus y square.
Yes,
Let's
yes.
take
We
x
write
square
z.
plus y
Yes,
square.
yes, yes. Yes,
Yeah,
sir.
you
Yes,
will
sir.
write it as z is equal to 0 is the plane.
Right. Yes, sir. Yes, sir.
Because its graph lies in R3. So
Yes,
the
sir.
tangent
Makes sense.
plane also lies in R3.
Yes, sir.
So
Makes
you'll
sense.
get a new
Yes.
variable. Its dimension is still 2, the dimension
Yes,
of
sir.
the plane.
Yes, sir. But the variables will be 3. Right, sir. Yes,
There will be 3 variables, and since there is an equation, you'll get the reduction of dimension by 1.
2. Yes, sir. Makes sense.
So that's it about tangent planes, lines, and all that. So critical points still remains. So hopefully, and that's not a very big topic. So maybe something like the first 30 minutes in the next session I'll spend on critical points, and then I'll show some things like how do you visualize this, or uh, let's see in the next
Sir,
session it will be
next
mostly
session is on
visualization.
Thursday, no,
It's
sir.
on Thursday. Yes, it's on
But
Thursday.
the deadline is
Uh,
on Wednesday, no, sir.
is it?
I'm not sure, sir. Sorry, sir. No. I think it's on.
Yes, sir. Actually, deadline is on Wednesday, sir.
Oh,
I think I'm assuming.
when did that happen? Uh, okay, there
Can we
must
have
have been
another
some missing.
session on Monday, Tuesday? Can we have another session, sir?
Tuesday, we are already having a session.
No,
Tuesday is a
from
TA
you, sir. From
session.
you, particular.
Tuesday and Monday and Tuesday I won't be available. I'll discuss with Lavanya and I'll let you know. So there will be
Sure,
a
sir.
TA session as usual on Tuesday. So you can maybe I'll tell him to cover critical points, whatever is required for the assignment. Let's get it out of the way. But I'll cover critical points again on Thursday as well. And yeah,
Sure, sir.
visualization of all of these things is for the assignment at least is not necessary.
So you can
So
ask the
Yes,
TA to also cover the left part, so that at least we can do the assignment, right?
yeah, that I'll do. If
Okay.
it's not possible to have a session before that, then I'll tell the TA to cover the critical points.
sure, sir.
Yeah, and as you can just try to have access to a computer or a laptop or whatever system that you can use GeoGebra on, so that you can also do for the next session. This is so that you can also do these things along with me.
Sir, in GeoGebra, how to draw the graph for suppose function x of y and the function is x square plus y square. For single
Just
variable,
write.
able to draw, but for two variable, not draw.
There's GeoGebra 3D also. GeoGebra 3D will allow you to do that. You can just Google GeoGebra 3D and there you'll get the 3D calculator. There you can write z is equal to x square plus y square and it will work.
So for the multivariable, we can do that, right, sir?
For up to two variables, of course, but beyond that, it's not
Understood.
possible.
Understood.
Right? Okay then. See you on Thursday.
Sure, sir. Okay, sir.
Thank you.
Thank you, sir. Thank you.
Thank you, sir.